Hey everyone, welcome to the video over logarithmic functions. So logarithmic functions and exponential functions are inverses, which means that they are symmetrical about the line y equals x. So remember, inverses are symmetrical about the line y equals x. Remember also inverses, in order to graph them, we can just switch their x and y values, which means their domain and range are flipped. Okay, the function f of x equals log base b of x is a logarithmic function with a base b. So how to pronounce this is log base b of x. And then the definition of a log says that if y equals log base b of x, if and only if b to the y power equals x, where b is greater than 0, meaning it can't be negative, and b cannot be 1. And x also has to be greater than 0, meaning it cannot be negative. Now, there are two special logs that we talk about. Okay, the first one is the common log. Okay, this is a base 10. It basically looks like a log with no base. So this is what you're going to see for a base 10. It's just going to say log of x. Again, it's assumed to be a 10. So if you ever see a log without a base, it is a base 10. Then we have the natural logarithms. This is a base e. It uses ln. Okay, so you will see it look like this, ln for the natural log. Now the next part is just switching from logarithmic form to exponential form. Okay, so it's important to know where each thing goes. So my base becomes the base of the exponential. What it's set equal to becomes the exponent, and then the x is what we set it equal to in the in the exponential form. So here we go on example A. Our base is 2. So my base of the exponential is going to be 2. What it's set equal to is going to be my exponent, which is 3. So 2 to the third power. And it's going to equal what is with the log, which is x. And that would be switching it to exponential form. Okay, so looking at my next one, we have x plus 2 equals log base b of 9. So my base is my base of the exponential. What it's set equal to becomes my exponent. So x plus 2 will be my exponent. And we set it equal to what's with the log, and what's with the log is 9. So we have b to the x plus 2 power equals 9. Looking at my next one, okay, I see that I'm using the natural log. Remember up here we said the natural log is a base e. So if you need to rewrite it as log base e of 4 equals y, then rewrite it like that so it helps you see it. So my base is e. I set it, my exponent is what it's equal to. So I have e to the y power, and I set it equal to what's with the log, which is 4. So e to the y power equals 4. So go ahead and pause the video and try D, E, and F. So you should be checking your work right now. So D is log of 100 equals 2. So notice how we don't see a base. That means that it is a base 10. So we have 10 to the second power equals 100. Looking at letter E, we should have log base 7 of to the third power equals 343. Looking at letter F, we have P equals log base B of n. So my base is B. I set it equal, or the power, or the exponent is going to be P, which is set equal to n. So hopefully you did those correctly. If not, write down any questions you may have so you don't forget to ask them. Now we are converting exponentials to log, so we're just going in the opposite form. Again, I have the conversion formula right there to help you. So here we go. We have our base, which becomes the base of the log. Then our exponent is what we set it equal to. And lastly, x, it goes with the log. So when we do these, we start by writing log, okay? But I notice in A, that is a base E. So instead of writing log, I'm going to write the natural log because that is a base E. And it's going to be the natural log of x equal to the power of pi. So again, the pi and the x. Looking at the next one, I have log of my base. My base is q of 19 equals the exponent or the power of 3. So again, it's just a lot of switching back and forth. Next one, we have a log and it's a base 10. So we can just write log and we don't have to worry about writing a base because it is a base 10 of 6, which is equal to the power of z. Okay, so go ahead and pause the video and try D, E, and F. So hopefully you gave it a try. So let's see how we did. We have log base 3 of 243 equals 5. Next one, we should have log base 9 of 81 equals 2. And last but not least, log base B of n equals p. So now that we've understood that, we can get into the graphing of log functions. So since log functions and exponential functions are inverses, we can graph logarithmic functions by switching the x and y coordinates of an exponential function. That's actually going to make it easiest on us. So if we look at example 3, we want to graph f of 2 to the x power. So I'm going to make a table so we can graph f to the 2x power. So I have my x, and then I have my f of x, which is equal to 2 to the x power. So I'm going to use -2, -1, 0, 1, and 2 as my x values. So I plug in. I have 2 to the -2nd power. When I have a negative exponent, that means I can switch it to the denominator, which gives me 1 over 2 to the 2nd power, which is 1/4. Then I have 2 to the -1st power, which is equal to 1 over 2 to the 1st power to get rid of the negative, which is equal to 1/2. I have 2 to the 0 power, which is equal to 1 because any number except 0 to the 0 power is 1. Then I have 2 to the 1st power, which is 2, and 2 to the 2nd power, which is 4. So I'm going to go ahead and plot those points. So I have -2, 1/4, which is about right there. I have -1, 1/2, which is about right there. And I have 0, 1, 1, 2, and 2, 4. So what we're going to do is connect the dots to the best of our ability. Should look something like that. Okay, remember that exponential functions have a horizontal asymptote. This one is at 0, so it's not going to cross that x-axis, but the domain is all real numbers, and the range is 0 to infinity, with 0 not being included. Now we're going to graph g of x. But to graph g of x, all we're going to do is switch the x and y of f of x. So we have x and we have our g of x. So for the first point, all we're going to do is we're going to take negative 2 and 1/4 and switch it to 1/4 and negative 2. Then we're going to take negative 1 and 1/2 and switch it. So 1/2, negative 1. Then we're going to take 0 and 1 and switch it. So 1, 0. We're going to take 1 and 2 and switch it and get 2, 1. And last but not least, we're going to switch 2 and 4 and get 4, 2. So now we're going to graph those, and I'm going to make sure I graph it in blue. So 1/4 negative 2 is about right there. 1/2 negative 1 is about right there. 1, 0 is right here. 2, 1 is right here. And 4, 2 is right there. So all we're going to do is we're going to graph this function right here. So it should look something like that. So these are inverse functions. Remember, inverse functions are symmetrical about the line y equals x. So I'm going to draw that in so we can see it. There is a line right there, y equals x. So it does look like a mirror image over that line. Okay, so since the exponential function has a horizontal asymptote at y equals 0, the log function is opposite of that, which means it has a vertical asymptote at x equals 0. The domain of the exponential function is now the range of the log function, and the range of the exponential function is now the domain of the log function. So their x and the y values just literally switch, which now leads us into our key features. So the key features of a logarithmic function. Again, it is opposite of the exponential function. So whereas our domain was all real numbers for the exponential function, that is now our range for the log function. Our range is all real numbers. Negative infinity to positive infinity. It's going to keep going up and it keeps going down even though it doesn't look like it on this graph. Okay, and the domain is what changes. It now starts at that vertical asymptote at 0. So our domain is all real numbers greater than 0. So we can say 0 to infinity, making sure 0 is not included. We can say x is greater than 0, or we could say it in words, all real numbers greater than 0. Okay, all three of those are the exact same thing. Now on this right here, we do have an x-intercept now. It is at 0, 1, or 1, 0, I'm sorry. And this time, because our asymptote is vertical, we do not have a y-intercept, it is none. And now my vertical asymptote is at x equals 0. So the important thing to know is that vertical lines are x equals. So when you see vertical, it should be x equals a number. The only time the vertical asymptote is going to change from 0 is if we have a transformation that is moving it horizontally. Okay, so now that we talked about that, we're going to move into our transformations. Transformations are the exact same as every function we've talked about so far this year. So we have A, C, and D, where if A is negative, it causes a reflection over the x-axis. The absolute value of A, if it's greater than 1, it's a vertical stretch. If the absolute value of A is between 0 and 1, it's a vertical compression. If C is plus C, it goes to the left C units. If it's minus C, it goes to the right C units. Then if D is positive, it goes up. If D is negative, it goes down. And last but not least, I added this in, A negative x is a reflection over the y-axis. Now you do have to be careful with that because if there's something with c, you do have to distribute that negative. Okay, so let's look into our two examples. On example number 4, it says transform the f of x equals the natural log of x by reflecting it over the x-axis, moving it 8 units to the right and 4 units up to create h of x. So we're going to start with our base function right here. So it's going to be the natural log of x, and we're going to add in everything we need. So first we're going to reflect it over the x-axis. So to reflect it over the x-axis, it means I put a negative out in front. Moving it to the left, moving it to the right 8 units, moving it 8 units to the right means that we're going to have a minus c. So it's going to be a minus 8. And then we are shifting it 4 units up. So that is going to be a plus 4 on the outside. And that would give us our new function h of x. Okay, now this next one is like something you're going to see on the test. If f of x is equal to log of x minus 2 plus 3, transform f of x 9 units to the left and 5 units down. Well, first off, we need to understand how it's currently moved. So this right here currently goes 2 units to the right. So if it's 2 units to the right and I want to move it 9 units left, I need to subtract those two numbers, and I'm going to get a positive 9, which means if a positive 7. So when I take this function to get g of x, okay, right now I have 2, okay, because I'm 2 units to the right and I subtract 9, that's going to give me a negative 7. And so since I moved to the left, then I have to have it positive. So I have log of x, and this is now going to become plus 9. Not plus 9, sorry, plus 7. Okay, because we took away the 2 units from the right, and then we only had 7 more units to go to the left. Okay, then we're moving this right here an additional 5 units down. Right now it's 3 units up. So if I'm trying to move it down 5 units, that means I have the 3 and then I only have 2 left, so it's going to be a minus 2 to get that right there. So this function right here has been transformed 9 units to the left and 5 units down to create a new function. If you have any questions, please make sure you write them down so you can ask me the next time I see you in class. Have a great day.